Welcome. Right now we're going to be talking about ideal gases, ideal versus real gases. So of course, when you think about things that are ideal, it would be the best of all possible circumstances, which is not always reality. So when we talk about gases that are ideal, we try to eliminate some of the factors that would, prevent us from making grand generalizations. Whoops. So an ideal gas will not have attractive forces between molecules. And they also can be obtained, the idea of them can be obtained if you are under certain conditions. So temperatures that are high and pressures that are low. Think of your ideal day would be like an ideal day at the beach. High temperatures and low pressures. So, we talked earlier about how gas particles should not attract, and they shouldn't, but maybe sometimes there's a little bit. So in order to make these generalizations, we have to talk about them as being ideal. And so the way that we could make a real gas act like an ideal gas is at conditions of low pressure and high temperatures. Okay, that's important. So I think of my ideal day at the beach. We've been talking about pressure a lot, but I suppose we should probably define what it is. Pressure is a force exerted on one unit of area. So in the metric system, or SI, it would be a Newton divided by meters squared. So Newton meter squared is a Pascal. So remember, we've talked about kilopascal. That would just be 1,000 times larger. And Newtons measure force, and meter square would be the area. So pressure is force, that's our Newton, over our area, which is meter square. So here is a calculation. What pressure is exerted? Let me get my calculator. I was unprepared. What pressure is exerted when a book weighing 19 newtons with an area of 5.22 times 10 to the negative second meter lies on the table? So if you think about it, a textbook laying on a table, will it have a lot of pressure? Well, it depends. If you're an ant and that book is on top of you, I'd say sure. If you're a human being, depending, it may or may not. A book could weigh heavily on you. So pressure is 19 over 5.22 times 10 to the minus second. Some people get scared of scientific notation, so how about we put it in the standard form? 1, 2. So 0.0522. So 19 divided by 0.0522 is 363.9 Pascal. Which would be, 0.363 kilopascal? It's pretty small. Okay. This formula is not found in the reference tables. You won't need to worry about it on the regions. Vapor pressure. So let's talk about vapors. Vapors are substances that are normally solids or liquids at room temperature that can enter the gas phase. Have you ever had Vicks Vapo Rub? So that is like a cream that you can put on your chest when you have a cough or cold. I've read online that you could put it on babies' feet and it'll help when, underneath their PJs, and it's supposed to help. I don't get that one, but anyways, when you put it on your chest, it warms up off your body temperature and you're able to breathe in these healthy kind of vapors, these gases. It's like a mentholyptus, I think they call it. So it's like a minty, but it's like eucalyptus. I don't know. I don't work for Vicks anyway. But that is in the jar. It's a solid, and then it becomes that gas when it's warmed up. Okay, and it enters the gas phase. It's not a container of gas. So the vapor pressure is the pressure that a vapor exerts. Also, let's go back for a second. Water has a water vapor. Okay, so a vaporizer creates a water vapor. Water is not usually a gas, can be, but it'll make it that way. So when we talk about vapor pressure, the stronger the intermolecular forces, the lower the vapor pressure. The weaker the intermolecular forces, the higher vapor pressure. And let's think about it. If the forces are holding molecules strongly together, they're not going to be able to go to the gas phase very easily. So there'd be less in the gas phase, so there'd be less gas particles pushing around on each other. So the vapor pressure would be lower. If there's a weak intermolecular force and it's like, it's sort of pulling them together, that means there would be more particles able to hit the sides of a container and have a higher vapor pressure. When vapor pressure of a liquid is 101.3 kilopascals, we call that substance boiling. Okay, so actually, boiling doesn't have to be at 100 degrees Celsius for water. It could be at a different temperature as long as you have the pressure at 101.3 kilopascals, which is kind of interesting. So here we have reference table H. This is in your reference tables, obviously. There are 4 liquids. And notice we have vapor pressure on the Y in kilopascal, and we have temperature on the X in Celsius. The scale of the X goes up by 5 degrees Celsius, and the scale on the Y goes up by 10, so be careful. These are 4 liquids that aren't normally vapors, but they can be at, they can turn into vapors. And notice the dashed line right here, this 101.3 kilopascal. That's the normal boiling point. So at standard pressure, wherever you see your curves cross, that dashed line will be the boiling point. So you would just find it and travel down and going down. What is the vapor pressure of water at 105? Now this is just reading the graph. 105 degrees Celsius. I'm going to travel up until I hit water, and then I travel over. And since I know that the y-axis goes up by tens, it's going to be 100. Hold on, does it go up by tens? Yeah, it goes up by tens. So this is 120 kilopascal. The vapor pressure of ethanol at the normal boiling point would be, the vapor pressure at boiling point is going to be that 101.3 kilopascal. Okay? Which substance will have the greatest intermolecular forces of attraction between molecules? So the greater the intermolecular force, the longer it's going to take until it gets to that boiling point. So which substance is going to have the highest boiling point? And that's going to be ethanoic acid. Because the stronger the forces are, the more heat energy, the higher the temperature it's going to take for that vapor to go and get into the gas phase. So we want that one, ethanoic acid. All right, thanks for watching.